Welcome in Cairo. Today we are going to continue our points for chapter 2 for the vibration of strings. Let's start by this question. Here in this question, give reasons for in the stringed musical instruments, the thin string produces sharp sound of high frequency, sharp sound of high frequency, while the thick string produces thick sound of low frequency. Of course, as you know, the relation between the frequency and the radius is inversely proportional. So, from where we know this relation? From this relation. Mu equals n over 2L times the square root ft over m. M here, the mass per unit length, equals rho density times pi r square. So the relation will be, yes, r squared comes out from the root, will be r. So the relation between the frequency and the radius is inversely proportional. So the frequency of the string is inversely proportional with the radius of the string. And therefore the thin string gives sharp sound of high frequency, but the thick string gives low frequency of harsh sound or rough sounds. That's for this question. What about these graphs? Of course, these graphs represents here the velocity on y-axis in meter per second on y-axis, and here the square roots of tension force on x-axis. What's about the slope? Of course, you know the relation to calculate the velocity of propagation, the propagation velocity in the stretched strings. From this relation, v equals square root ft over m. So the slope here equals delta v divided delta square root ft. So here v divided, yes, square root ft, it will be, yes, 1 over square root m. That's the slope for the first graph. What's about the second graph? The second graph here, we have here on the y-axis the frequency nu in hertz, and here in x-axis 1 over L meter power negative 1. So if we make a division to calculate the slope, frequency divided 1 over L, it will be, yes, nu times L. So nu times L equals, yes, v over 2 or square root ft over m divided 2. The half square root ft over m, or velocity divided 2, where the v is the velocity of the wave. That's for these graphs. And now with the examples, look here. In this example, we have 1 meter string whose mass is 1 times 10 power negative 3 kilogram. This string is under tension of 20 kilogram weight. So we have 20 kilogram weight, we have to change it to Newton times, yes, 9.8 meter per second square. So what is the fundamental frequency? First of all, we have to calculate the mass per unit length. Mass per unit length, m small, equals mass of the string divided length of the string. Mass of the string divided length of the string. Mass of the string here equals 1 times 10 power negative 3 divided length of the string, which is 1 meter, so it will be 1 times 10 power negative 3 or 0.001 kilogram per meter. That's for the mass per unit length. What's about the tension force or force of tension? Force of tension or tension force, we have 20 kilogram weight times 9.8, it will be 196 Newton. So to calculate the frequency nu equals n divided 2L times square root ft over m. Nu equals n divided 2L times square root ft over m. So nu equals n number of segments, which is 1, divided 2L, 2 times length of string, 2 times 1 times square roots ft 196 divided m, which is equals 0.0001. So the final result for the frequency will be 221.26 Hertz. That's for this example. Let's move to another example, which is a string from steel wire, its length 1 meter, vibrates in two segments. Vibrates in two segments. If it is stretched under a tension of 8 kilogram weight and G equals 9.8 meter per second square. Calculate its frequency. Calculate its frequency given that the mass per unit length of the string material is 0.001 kilogram per meter. First of all, we have here, yes, the mass per unit length. We have the tension force, but the tension force we have to calculate it. We have to multiply, yes, 8 kilogram weight times 9.8 meter per second square, so it will be 78.4 Newton. And the number of segments here is 2 segments, and the length of the string is 1 meter. So nu equals n divided 2L times the square root Ft over m, so it will be as follows. Yes, frequency equals to 180 hertz. Let's move to another example, which is here a string is under a tension of 10 kilogram weight. Its mass per unit length is 0.01 kilogram per meter. Calculate the velocity of propagation of transverse wave in this string if G equals 10 meter per second square. First, we have tension force in kilogram weight. To change it in Newton, we multiply it by 10. So tension force equals 10 times 10 equals 100 Newton. Mass per unit length equals 0.01 kilogram per meter. From the relation, velocity equals square root Ft over m. Velocity equals square root Ft over m. Ft tension force divided m mass per unit length. So velocity equals square root tension force 100, and the mass per unit length is 0.01. 100 divided 0.01 under the root, so it will be, yes, 100 meter per second. That's for this example. Another example, a string of length 1 meter and mass 1 times 10 power negative 3 kilogram is stretched with a mass of 200 kilogram. Acceleration of gravity is 9.8 meter per second square. Find its fundamental frequency. Find its fundamental frequency. Here, to calculate the mass per unit length, the longitudinal density, mass per unit length equals mass of the string divided length of the string. Mass of the string divided length of the string. So, m equals mass of string divided length of string, 1 times 10 power negative 3 divided 1 equals 1 times 10 power negative 3 kilogram per meter. That's for mass per unit length. And for the tension force, mass of weight times gravity acceleration. Mass of weight here equals 200 kilogram weight. Divide times 9.8, it will be 1960 Newton. 1960 Newton. From the relation, nu equals n small, number of segments, divided to L times square root Ft over m. So 1 divided 2 times 1 times square root 1960 divided 1 times 10 power negative 3. So the frequency nu equals 700 hertz. 700 hertz. After that, we have another example. Here, a string of 60 centimeter long and its mass is 0.3 gram emits its harmonic tone of frequency 280 hertz. When it vibrates as 2 segments, so it is, yes, first overtone or second harmonic tone. Find the tension of the wire. First of all, m equals mass of a string divided length of a string. Mass of a string is 0.6 gram, but we have to change it in kilogram. So 0.3 times 10 power negative 3, 0.3 times 10 power negative 3 divided length of the string. Length of the string here 60 centimeter. 60 times 10 power negative 2. So 0.3 times 10 power negative 3 divided 60 times 10 power negative 2. It will be 5 times 10 power negative 4 kilogram per meter. That's for the mass per unit length. So from the relation, nu equals n divided to L times the square root Ft over m. So nu equals 280 hertz equals n number of segments 2 times L, 2 times 0.6 0.6, 60 centimeter times 10 power negative 2 to be in meter, so it will be 0.6. Okay, times square root FET divided 5 times 10 power negative 4, the mass per unit length. So we have here 280 divided 2. After that, the result 140 times 2 times 0.6. After that, we make a squaring for both sides to remove this root, to eliminate this root. So after that, we make cross multiplication to calculate the tension force. It will be 14.11 Newton. 14.11 Newton. Another example. Transverse waves travel with a speed of 15 meter per second. Transverse speed of 15 meter per second. In a string under tension of 5 Newton. What is tension is required for a wave speed of 25 meter per second? Here the relation between the velocity and the square root of tension force. And of course the relation between them is directly proportional. So here V1 over V2 equals square root Ft1 over Ft2. Why? Because this string is not changed. It is the same string. As it is the same string, so the mass per unit length is not changed. The same string, so the mass per unit length is not changed. As I told before, the relationship between velocity and tension force, the root of tension force, is directly proportional. So V1 over V2 equals square root Ft1 over Ft2. So 15 divided 25 equals square root 5 divided Ft2, squaring both sides, cross multiplication to get Ft2. So Ft2 equals 13.889 Newton. 13.889 Newton. At the end, I want from everybody, I hope from everybody, to understood our points for today, for this chapter. Thank you. See you later. Goodbye.